We come today to uses of alkoxide in processing. Before I start, let me have a recap of what we did earlier. Is we had a solution, alkoxide based, where a sol was formed. Now by refluxing we formed a gel. This gel, when dried, gave a zero gel. And this is slow evaporative drying. However, if this same gel was dried hypercritically, we would get an aerogel. This gel evaporative drying and it forms a body, and then when sintered gives a dense gel. Now if I look at the screen over here, if I look at the screen, this is an example of an aerogel, which is very lightweight, very porous, and you can see it's insulating. There is a blowtorch at the bottom and there is a flower on the top, and it is not melting. These aerogels were formed, as I said, by hypercritical drying. An example of this zero gel in use, aerogel in use, is in this one. This is a material which is sent up by NASA as a stardust collector, which collects, which is trying to capture the dust in space. And this is basically an aerogel, a very lightweight body. You can look at through this aerogel, you can Google and find out various structures of aerogel and its various uses. If I key in zero gel, I'll have again this structure, which basically is showing that when the silica alcoa gel, that is a alkoxide sol, was dried, it shrinks to give a silica zero gel, and when this is sintered, it will give a very dense transparent body. Now this is what I had covered until the last day. Today I shall be talking of using these alkoxides for developing different coatings. All of you have seen in today's high-rise building, which are mainly of concrete and glass, and there are other steel and glass buildings coming in, which have highly tinted glasses. These glasses can be for various purposes like heat reflecting, light reflecting purpose. These glasses are made by physical vapor deposition process. That is, and these physical vapor deposition processes are very capital intensive. They are intensive in terms of electricity, also usage of electricity. Moreover, problems arise when, say, you have got tall skyscrapers and they have to be cleaned because dust collects on it. Physical vapor deposition processes of coating glasses have been unsuccessful in developing glasses which need not be cleaned. Let me try to introduce you to some of those processes and technologies. Like, say, let's talk of a very simple process, dip coating. That is, what we do is we take an alcoa sol, which is basically the alkoxide which has been hydrolyzed. It has not yet formed even a semi-rigid gel. It is a process, and there I dip this plate in and then withdraw. As I withdraw the plate, what happens? This alcoa sol would stick to the surface of the plate, and as I raise it further, the plate is now covered with this sol on both sides, alkoxide sol on both sides. The solvent dries off, leaving behind an substrate with a coating of the dried alkoxide gel. Now, it has to be then heated and sintered. But before I get into that, let me look at it in a little more detailed fashion. In a dip coating process, when I have dipped the plate, withdrawn it totally, let me look at the surface structure. This is the substrate, and this is the liquid coating on it on a very exaggerated scale. Now, one has to remember that as I am withdrawing it, evaporation of water and alcohol will be taking place, and at the same time as it takes place, gelation also occurs in this layer. In order to control the thickness, it is very essential that this whole process be done under controlled atmosphere. And over here, where the tail end, as the substrate is being withdrawn, this level, at this particular level, I will have aggregation, and here film formation is prevented by surface tension. So, unless I pull the whole substrate out of the liquid, I will not have a coating. I will always have this sort of aggregation. So, what we have to do is put the substrate in and then slowly pull it out till it is out of the entire liquid surface. Now, this thickness of coating, this coating thickness will be dependent on the speed at which I withdraw this substrate, that is withdrawal speed, and also what is the amount of the gel in this particular liquid. So, this is the solid content and hence viscosity of the liquid. These are the two factors which will control the coating thickness. Now, one of the most important things is during this withdrawing, that is, if I put in an additional diagram over here where I had the liquid, the liquid surface would be bent. During this withdrawal step, it is very, very important that no turbulence occurs. No turbulence occurs. Otherwise, we will have a real random mixture. So, if the dip coating process is correct and if the withdrawal is such that there is no turbulence, that the system stays in the Newtonian regime, no turbulence in the Newtonian regime, then the thickness of the coating is given by this equation. Eta is the viscosity. Eta is equal to viscosity. V is the velocity of withdrawal. Rho is the density, and G is the gravitation force. So, this particular equation gives us the thickness of the film. Now, one thing I have forgotten to mention was what is this? This is the liquid vapor surface pressure, gamma LV, surface interaction. Now, this is a rough estimate of the thickness. Now, let us crudely assume, let us very crudely assume that as we are starting to dip here, from here to here to here to here, as we are withdrawing, the evaporation rate is constant. In that case, first of all, the evaporation rate is evaporation is always occurring right from we start withdrawing. In that case, the final thickness which we will see is given by something like this: 1 minus rho A, rho 0 by rho A. Rho, what is rho 0 by rho A? Rho A is mass of volatile solvent per unit volume at the very start. This is rho 0 A. So, the equation is 1 minus rho A 0 by rho A multiplied by 3 eta viscosity. E is the evaporation rate. E is the evaporation rate divided by 2 rho 0 A omega square. And hence, what we have over here is H is really a factor of C and omega minus 2 to the power of 3. So, this H final is really dependent only on this factor, that is the withdrawal rate. And this, hence, this withdrawal rate needs to be controlled. Let me show you a slide where here the person will simply immerse his hand into water where there are carbon nanotubes forming this pattern. Watch it, what happens? He immerses his hand in the water, takes it out, and his whole hand is coated with carbon nanotubes. Now, dip coating is this good a process where you can have monolayers of coatings on any surface you want, provided you control the atmosphere, the viscosity, the withdrawal rate and the temperature. Another mode of dip coating is this angle dependent dip coating. This has its advantages in the sense that the coating thickness is dependent on the angle between the substrate and the liquid surface. Here you have got much more larger surface area exposed to the liquid. If you compare this, if it was vertical, how much would it be? Much smaller. So, this gives it, and by this particular angle dependent dip coating process, where we can also rotate the substrate we get excellent thin film coatings by this particular process. Another way of working around would be spin coating. Basically, if I look at spin coating, it would be this, that I have a substrate on which a drop of liquid forms, is dropped on the surface. This is spun around and this liquid spreads all over the surface. This is a spin coater. I will show only selected parts because this is a spin coater. It is being opened. What it has in the center is basically a holder with an O-ring, and the gentleman places a glass plate on it, and then he evacuates it, so that the glass plate is now sticking on the surface of the rotor. He closes the machine and then he fixes up various parameters through which the solution is sprayed from the top. Here the rotor is rotating and solution is sprayed onto the surface right from the top. This is the basic spin coating process, a very fast, very efficient process. However, I would like to show you another one, and this is a very small one, but what I want to say is, once I have dropped the liquid on the surface and I am spinning, what happens on the surface? And this one is an elegant picture of what happens. You have to, this is a very short one, so you have to look at it. This is spinning, a liquid drops and it spreads, and finally it forms an uniform coating. So during this process, what is it that happened? During this process of spin coating, what happened is that here, what happened is, this is the cup, this is holding the substrate surface, and the liquid has dropped. When you start spinning, these wave fronts were generated because the liquid tries to move away from the center and generating the waves which you saw in the last one. So here the liquid, as you keep on adding more and more, this wave front forms and the extra liquid goes away, finally leaving a thin coating of liquid on the surface. If you, in real spin coating process, a couple of drops are added and then this sort of a surface is generated. This spin coating can be classified into two. One is a deposition, where the drop is allowed to fall on the surface. Then it is spun, the spin up. During the process, the liquid spreads itself on the surface. Then is the spin off, where depending on the viscosity and the addition of the liquid to the substrate, the liquid flows, the extra liquid falls off, forms a thin adherent coating, and then evaporation occurs. You see, in the video that I showed you, spin coating is a very easy equipment to handle, but the difficulty is the viscosity, the solids loading, and the adhesion between the two surfaces, that is the liquid and the substrate, has to be controlled very, very rigorously. If I try to determine, because if spin coating is so helpful a material, then I should be able to model it so that I can get reproducible coatings. This plastic lens of mine has a hardened spin coated coating made by the process I have just described. Because this is a plastic lens, it could scratch easily. So, the surface has to be hardened, and this glass has an alkoxide derived coating, so that its surface does not scratch easily, and it was made using this very process. And hence, it is very important that the modeling be done so that the surface thickness can be rigorously controlled. The real thickness that we can control is up to the spin off. So, here the value of H is after the spin up, what was the thickness, that is H0, 1 plus 4 rho density, omega square angular velocity, H0 square, H0 is the original thickness, T is the time divided by 3 to the power eta, and the whole thing to the power of half. Now, this spin coating process here, ultimately, again, if everything is constant, then you will see the thickness is inversely proportional to the momentum, the speed at which it is being rotated. So, here we need to control the density, that is the solids loading, the viscosity. These two are in our hands. The adhesion property is something that we can use by changing the type of mixtures. For example, if alkoxide derived coating is made from, say, aluminum nitrate, what we will have is a very, very good aerogel. But if the same thing is made from aluminum chloride, we will have an aerogel which is much more transparent. This is because the type of the starting materials control the rate of hydration. Now, I have talked of dip coating using alkoxide based materials. It is being used extensively in many areas. Spin coating, alkoxide derived materials being used in many areas. How does it score over physical vapor deposition process? At the right outset of today's lecture, I said the current coating technologies of glass suffer from certain infirmities. Like using them, we have not even been able to fabricate dust repellent windows. However, using alkoxide based process, dust repellent windows have been fabricated. All of you have seen lotus leaves. Lotus leaves do not collect dust, neither can water settle on it. And I have discussed this earlier, much before in my class. Today, sol gel coated windows for architectural purposes are being manufactured and marketed. They are made by using, for example, zirconia based alkoxide, ZrO2 based alkoxides, so that on the surface of the glass there is a ultra thin porous coating of zirconia, which gives it two properties. Zirconia makes the surface harder, it is less scratch resistant, because say 300 feet up in the air velocity can be very high and the dust can also abrade the surfaces. So, we needed a surface which will be scratch resistant by dust, which flies at a high velocity, say 300 feet up in the air. So, they have a very thin, almost nanometer, 10 nanometer level porous zirconia coating. It is not 10, it is 100 nanometer level, porous zirconia coating. Now, after the zirconia coating, what they have done is filled it up with fluorosilanes, so that the surface of the coating looks like this is the porous zirconia coating. This is a glass window. Remember, this scale I talked of was in 15 nm or so, and this porous ones, they are filling it with fluorosilanes, so that the surface looks something like this, exactly a lotus leaf structure. Lotus leaf structure. Hence, this surface is self cleaning like lotus leaf. Alternative methods are being sought to replicate. For example, you have got paints. Today, a lot of companies market paints which they say are self cleaning. You have seen buildings whose color remains white even now, even after years. What does that paint have? That paint has titanium dioxide. The way the titanium dioxide works is, if this is the inner and this is the outer surface, normally what happens, rain, everything falls on this outer surface, and there is, this surface starts turning black due to organics. In today's paint, what they have is they coat it with nerolac, or they call it weather resistant paint. The main constituent is ultra fine titanium dioxide. This titanium dioxide reacts with sunlight and oxygen, giving you ozone. This ozone reacts with all these organics. It literally burns away the organics, leaving the surface absolutely clean. So, today's nerolac weather resistant paints, they stay year after year white due to the presence of titanium dioxide, which under the action of sunlight and oxygen forms ozone, and this ozone simply burns off these organics, hence the surface stays white. So, in today's glass technology for architectural purpose, people are trying to now put in, this is the glass body, have titanium dioxide coating over here on the glass body, so that this coating can help burn off the organics which deposit on it and cause the glass to become hazy. However, as I said, this is something that people are looking at, but self cleaning glass is already in the market, and that has been made using porous zirconia coatings with fluorosilane, filling the pores so that the surface looks like a lotus leaf and water or dust cannot collect on it. Before I go further, in order to give you some idea, what are the different types of films produced by alkoxide or sol gel processing which are available in the market? Mechanical or chemical, as I said, for my spectacles, I need a hard coating on the surface of the plastic fibers. SiO2, tetraethyl orthosilicate. I have talked with it long. If I want optical coating which would absorb light, then I would go for titania, silica, with oxides of iron, chromium or cobalt. This is one, this is one. This will cause absorptive thin films, for example, absorbing sunlight where it is in cold places, where you want the infrared to come through and heat the room, so the room stays warm enough. So here these types of coatings, coated materials, are already available in the market. Whereas in our place, if we want reflecting coating, I do not want the light to come through or the heat to come through, indium oxide, tin oxide coatings by alkoxide based sol gel are now routinely available. If you are looking at anti-reflection coatings, frequently you have faced reflection problems, anti-reflection coatings, this sort of materials are already available in the market. Finally, the type of coating I was talking of for making windows which do not fog up with grime, dirt, dust of today's metropolitan cities, they are developed photocatalyst or titanium dioxide based coatings. So these are the areas you have understood, you are familiar with, and maybe you are more comfortable. Now let me talk of some processes where alkoxide based sol gel coating is being used very extensively. At times what is needed is either dip coating, I said, or spin coating. In both the cases, whether it is dip coating or spin coating, especially in dip coating, I am losing a significant portion of the solvent because I cannot use it. If I have a cup, I put a material in, I am using only say 20% of the volume of the liquid for the coating purpose. For spin coating also, I am using hardly 20% of the volume of the liquid. Now, given the high costs of these materials, this is unacceptable waste. So, how can we modify the so-called easier dip or spin coating process so that say 80% or more of the sol or the solution is really used? Now, let me come up with one process. Let's say we have a bath. This is filled with liquid right up to here, and over here we say have a solid shaft, that is this, or for simplicity's sake, let us say we have got a cylinder which can rotate in this direction, and the surface of the cylinder is such that when it rotates, it picks up this liquid. This top part gets coated with this sol as it rotates. So, as this cylinder comes up, this top part is coated with the sol. Now, over here, if I am using this one, I bring a substrate in. This is rotating, wrong direction, sorry, let me redraw it, wrong direction. If this is what has to happen, then I have done it in the wrong direction. This is the rotating cylinder which has picked up liquid as it is rotating. It is covered with a layer of the solvent as it is rotating, and now from this end I push my substrate in. What would happen at this particular point of time? If this substrate could be brought close enough, immediately this liquid layer would start covering the substrate layer. And if I move this slow enough, control the viscosity, control the velocity, rotational velocity, and I can keep pushing this substrate, what I would be getting is a very uniform coating of the liquid on the substrate surface. Now, this is due to capillary action. I had brought the substrate surface close enough to this meniscus so that the liquid, due to the surface tension, covered the substrate, got in touch with the substrate, and the substrate surface got coated. And as I keep pushing this substrate more and more in this direction, what I will have is a larger areas of the coated substrate. Now, in this particular process, we have 90% utilization of this particular sol. Now, the technology of alkoxide based processing is still in a nascent stage. Yes, sure, I have got a specs which is coated by alkoxide based process, but one of the things is we know that the evaporation rate has to be controlled, the loading has to be controlled. In this particularly capillary action, where the film layer is formed simply due to the capillary effect and the high surface tension, you have to understand that the evaporation rate will also be very high. And if you go back to my earlier lectures, I had talked of that is when a zero gel, if the evaporation rate is too high, the body shrinks non-uniformly and it will crack. And hence, today people are exploring a lot of these technologies for this alkoxide based sol gel processing, and so that a better utilization of this very expensive alkoxide based coatings can be made. Now, one of the things that alkoxide based coatings has given us is our ability to deposit say dielectric materials, barium titanate, on various substrates at very low temperature. So far, when we are talking of physical vapor deposition, all these dielectric coatings, the thin film deposition of these dielectric coatings was very difficult, because in physical deposition process, say the sputtering rate of barium titanate is entirely different from the sputtering rate of say strontium titanate, which is an essential component, or lead titanate, which is an essential component. As lead titanate pushes the temperature up and the strontium titanate pushes it down, so that the barium titanate bit dielectric has an uniform capacitance over a large temperature range. In sol gel processing, what we are now seeing is these complex materials can be deposited in some cases at very low temperatures. This ability to deposit say complex systems like BaTiO3, PbTiO3, SrTiO3, all of these are titanates, which and this particular system, and they can be we have got alkoxides of these and they can be processed. So thin film of this by alkoxide based processing looks very exciting, because here it is from one gel, one sol, where all the three are there in our desired ratio, we will get that particular coating. We would not have to have problems like physical vapor deposition. Using this technique today, and a very well known technique which is screen printing. Many of the colorful dresses you wear, be it in saris or in your salwars, many of the patterns have been deposited by screen printing. And screen printing plus alkoxide base sol gel technique have been used to deposit thin films on various substrates and even plastics. In that particular process, what is the screen printing process? In the screen printing process, this is a substrate which may be your sari, on which you want some regular print to be done. So what do? They have a screen on which the patterns are built in. Then the dye is poured over on the screen. The viscosity of the dye is such that it does not fall below. And then what is done? These two ends are held and a squeegee simply moves the dye along the surface. So when the squeegee presses, what would happen is this would happen, and the dyes would come out through these pores and stick to the surface of say your sari or whatever you are wearing. So this pattern on the screen can be repeatedly replicated on this particular sari or the cloth you are wearing. Now, alkoxide based sol gel technology has used this particular process to have patterns printed on substrates. It can be flexible substrates, it can be hard substrates, but this printing technique is used extensively. Here, this particular material is the gel of, say, what I was using, barium, strontium, lead, titanium, alkoxides. 4 metals, their alkoxides mixed together in the proper ratio, refluxed, so that they have the gel containing exact composition of the constituents. Yes, we do face problems when we are using such varied ones: barium, strontium, lead, titanium. What if their hydrolysis rates are different? That's a major problem. And I had talked of it much earlier. How can we solve such problems where the hydrolysis rates are different? But those problems are solvable, and using this alkoxides and screen printing technique, we can print structures onto different substrates depending on what we need. And this screen printing technology is very, very important. Another area where this one is used is very extensively. Let's talk of, a lot of people have heard it, fuel cell. Over here, the water is dissociated at high enough temperature in a ceramic container so that it dissociates to give you the hydrated oxygen, which is subsequently used as fuel. In many cases, these fuel cells have got multiple layers. Let's see if I can get some on the web. Now, here is, I have got various layers which are sandwiched one on the other. Water flows through one, the hydrogen goes out through another layer, oxygen comes out through another layer. Now, this whole assembly operates at a temperature, elevated temperature of there. Now, the whole assembly has to be sealed so that the gases don't escape. You have got very, very low channels, as you can see over here, and they have to be sealed so that the hydrogen can be collected efficiently. Would you be very surprised if I said that this whole fuel cell assembly can be sealed by immersing it in tetraethyl orthosilicate alkoxide media, so that the TEOS covers all the surface, fixes all the leaks, and that fuel cell now becomes leak proof, and it is what is being done. Alkoxide based sol gel processing is being increasingly used to make these fuel cells of the type that I have shown you here leak proof, and so that they can operate with much more efficiency. Another area where this alkoxide based sol gel processing plays a huge role is frequently in many applications we require multi-layer coatings. This can be used for many purposes. This is one layer, this is a substrate. On top of it, I have one layer. Here, I have got a second layer. Here, I have got a third layer. And then I repeat it all over again. I'm getting mixed up with the colors. This is blue and this one. Now, these coatings are now made by physical vapor deposition process. But as I said, physical vapor deposition process is turning out to be an expensive one. So, now alkoxide based sol gel processing is being increasingly used to deposit such layers. And which is the best process to deposit this one other than this capillary method? Because here I have got one bath, I deposit the first layer, let it dry, take it to a second bath, deposit the second layer, take it to a third, deposit to the third layer, and repeat the cycle as many times as we want. If we have got good control over the modeling aspect, the viscosity, the temperature and the evaporation rate, we are now able to generate multi-layer coatings using sol gel technology. Now, that is why bother about sol gel when multi-layer coatings are available? You see, yes, they are available, I won't debate it. But if someone wants to fool around with the with the layers, say change the composition or the relative amounts, doing that in the standard physical vapor deposition equipment is out of question. Because if a PVD system is using say component A, B and C for this multi-layer, no manufacturer will ever dream of trying A, B and D in the same unit because of contamination. This alkoxide based sol gel process gives the manufacturer the competitiveness that he can work with A, B and C fine, but if he wants to work with A, B and D, he does not have to worry about the contamination aspect. All that he has to do is invest the money to standardize these factors, temperature, viscosity, solids loading and hence evaporation rate, everything, and he can automatically change layers, experiment with layers depending on his whims. And this is coming more to the fore today, because today electrochromic windows which changes color depending on the potential, windows which changes color depending on your needs, as they are coming to be used more and more, the type of multi-layer coatings which are being required are changing, something that cannot be done easily in a standard fab plant which uses physical vapor deposition process. I have given you the links, shown you on the terminal screen. Where did I go? This is a field which is vastly open, is currently under development, and I guess you have to do a little bit of extra search if you want to know more about how alkoxide based sol gel processing is being increasingly used to replace the standard items available in commerce. Thank you.